let us begin today with the chill water pipe SLD drafting. And until now that we had seen related to the water side, now we are going to start doing the drafting skills for chill water piping water side along with the help of chillers. So until yesterday what we were dealing with was DX system, that is direct expansion. Today what we are going to do is with chill water pipe system. So what is the basic difference between the two? We know that one. DS system is not involving any particular extra external source for cooling measurement. Whereas the chill water piping is having the normal refrigeration compression along with the external chill water piping. With the means of water it is cooling more. Alright. So the chill water piping is also going to be totally centralized. And as we know, International Airport has many terminals. So this is a part of first terminal, terminal 1. All right. So that way we're going to see the chill water pipe designing for this one. Today we're going to deal with SLD. But before we even do the SLD, what we actually have to deal with is key. We have to understand key what way is the conversion between the TR and GPM and etc. Okay. So that way what we're going to understand very, very easily is I first need to ask you how much is 1 TR related to in terms of GPM. 2.4 GPM exactly. All right. So we know that the chill water pipe that we are going to consider is having connections going to deal with into which application. If the chill water pipe is going to be connected to which product or which element? AHU, right? It is going to be connected to the AHU. All right. So today what I'm going to explain before you is we're going to deal with some examples, and that way and after that we are going to understand how the chill water pipe is going to be connected inside the AHU, how the water is going to be supplied and how it is going to be returned back. Okay. So very quickly, I'm going to deal with the main designing standard, that is the conversion, that is 2.4 GPM. And if you are going to open your notes, and inside the notes we have a table that you have to follow at the time of suggesting the pipe size. Until yesterday we were dealing with 800 by 300 for the duct size. Now we have to take that in terms of a diameter, all right, in terms of mm or in terms of inches. So open the page number, I think inside your notes, yes, page number 30. And you can see it is a closed piping system and the complete all will on page number 30, so that it will become very easy for you to do the designing. Okay, so keeping this in mind, we know where it's located on page number 30. So you can keep this open and we can understand directly from the screen how it is going to continue. So before you, I'm going to create one AHU. I'm going to call that a 5TR. How much is 5TR in terms of GPM? How much would that be? Quick calculations, Kelsey is outside, and because we are going to do that very, very quickly. 5 into 2.4 in terms of GPM. Everything we are going to deal here in GPM. What is GPM? Gallons per minute. How much it is? 12 gallons per minute. So in this one, I'm going to create one green entry and one red entry, which is going to be the supply and return into the AHU. Down below is I'm going to deal with creating my chiller. I'll take water cooled chiller, and that is going to be 600 TR. Very quickly, how much in terms of GPM? Yes, 1440 GPM. And from here as well, we are going to have a connection green and a connection red. I think we already know why I'm taking green and red. Return and supply. So what happens is when you're going to make a connection, let me take a pathway. The water that is generated inside the chiller as per the drafting standard, it is going to be supplied to the supply of the AHU. And how is that same water coming back inside the chiller? By return from the AHU into the chiller. So let me draw one schematic diagram so that you can understand how the pipes are going to be linked. And this is another one. This is the flow inside, and how much flow will go inside the AHU? Only 12 GPM. From how much? 1440. So now minus from 1440, 12. How much will be remaining inside the chiller? 1428, right? 1428 GPM will be remaining inside the chiller once the supply is left for going to one AHU. Now you might be having not just one AHU. In between there can be another AHU connected like this. AHU, and I'm going to call that with 7.5 TR. How much in terms of GPM? Calculate 7.5 into 2.4. 18. So 18 plus 12 becomes 30 GPM. So at a time 18 GPM is going to be dropped here, and from 1440 the rest remaining will be moving forward and the 12 will be dropped there. So at the end of all the supply to the AHUs, chiller is still having some amount in bulk, right? And that is why you can see the content. This is 600 TR chiller and this is nearly single digit AHUs. They can be, as per the example, this is only example, you can have maximum of 10 TR, maybe 12 TR, 15 TR AHUs, depends, depending upon the application where you're working, airport or hospital or hotel, etc. What you need to understand is the moment 18 GPM is moved into this, 18 GPM will be accessed, and the rest, how much ever water was required for the cooling segment, that will be done inside the AHUs related to your evaporating coils and etc. And after that directly 18 GPM will be left back again in through the return pipe, and that will be moving back to the chiller. Directly the same situation is with this AHU. Maybe I'll call this AHU1, this AHU2. From both the AHUs, 30 GPM, 12 plus 18 is going to go back to the chiller. And if this return is not going to go back to the chiller, chiller will be left with how much? 1440 minus 30, 1410. 1410 means convert that into TR, divide by 2.4. 587.5 TR is remaining inside your chiller. All right. So why are we actually taking care of these calculations so deeply? Is because when your supply from the chiller is going to move, maybe your plan is going to have 10 AHUs at one instance. So now dependent upon the GPM level, okay, the GPM level is what you're going to decide the pipe size. Now we know that what is the main riser of a chiller? What is the main riser? Which pipe is called the main riser? From where the water is actually supplying, the main opening of the supply connection. So that can be, I can call that this is a riser, right? This is the main connection here, that the pipe is actually, the water is moving inside the pipe. All right. So from here, this is going to be your head, and this is going to be the individual supply into the AHU. Now, if I am going to mark the fittings, here is I'm going to get one elbow. I'm going to get one elbow here at the turning. This is another elbow, and this is another elbow. Nearly 4 to 5 fittings are applied. Clear? And in between, if I'm having an AHU, so this is going to be one different connection. This is going to be another fitting. We're going to talk about that a little later. Fine. So there has to be taking a turn. This has to go, and then it has to follow. Now from the table on page number 30, what you have to tell me is look for the table and search for 1440 GPM range and tell me what should be the riser pipe size. I'm going to open that again. Look for 1440 GPM range and tell me what should be the pipe size in terms of mm, not inches. 200 mm. That is the main riser size coming from the chiller. Now look forward for 7.5 TR, that is 18 GPM, and look for 12 GPM also. 12 mm. 12 GPM. So 32 mm, right? Yes. So if I'm going to come back to my, this is going to consider these 40 mm pipes are this one, the ones through which the water is moving into the edge. Now what will happen if I'm going to keep 200 mm of pipe here also, same as the riser? Can I only get 18 GPM? No, there is chances of more water flowing. Why? Because the orifice of the pipe is much more larger. All right. So I cannot do that one. The pipe size totally depends upon your GPM. That is why so much of calculation is required. Is it clear? And now in the table that you can see, not one particular standard reading of the GPM is given. There is given flow range. All right. Why? Because after we subtract, in this situation it becomes 587.4. It is 1410. Now 1410 is also going to range between 800 and 1700 on serial number 12, where we have suggested 200 mm. All right, if I'm going to calculate that for every GPM, the table would become very, very long. Is it clear? Now you calculation here. Now this much of connection is understood from the chiller, how the water is moving into individual HUs and all. Now I'm going to rub the whole thing and I'm going to draw that again. I'll draw one AHU. Now we are going to understand the levels. Considering the same example, 5 TR, 12 GPM, green, red, CH, 600 TR, 1440 GPM. One elbow, second elbow, third, fourth. Yes, now what we are going to understand is, after we understand that the supply of chiller is connected to supply of AHU, return of AHU is connected to return of chiller. Now, how does the propagation of water flow depending upon your levels? In the chill water piping, level understanding is very, very important. If you don't understand the levels, you're not understood anything with chill water piping. You will be left empty with the knowledge, right? So when I'm going to talk about levels, in the complete setup where the water is supplied and it is returned, listen very carefully and observe the drawing. The water that is moving inside the riser of the pipe of the chiller, the water that is moving inside the riser of the pipe in the chiller is called level 1. That is the main level through which the water is generating to flow. Clear? Now until the water is moving above, until this level, it is level 1. From here, what is having, the pipe size is changing. It is changing, right? Because it has to supply only 12 GPM. So this was, how much we considered that one? No, it was how much size for 1440? It was 200 mm. Yes, 200 mm. And here what we are going to consider is only 32 mm. I think so. 32 mm, right? 32 mm. So from 200 mm, it is reducing to 32 mm. So this becomes your next level, level 2. That is supply level. All the supply levels from the chiller to the HU is called level 2. And now what is the only parameter remaining? Return. Return becomes level 3. So what you have to understand is, every supply is from level 1 to level 2. Is it correct? From level 1, water is moving to level 2. Every return is from level 3 to level 1. Is this correct? Water is moving from level 3, moving back into the same pipe which is of level 1, and it is moving down here. Now you can see that I have drawn the pink color, magenta colored line over the gray colored line. This is to make you understand that if you are going to look at this complete setup from the top view, now since my level 3 is above level 2, and if I'm going to look at the pipe connection from above, can I see the gray color pipe which is below? No, I won't be able to see. Now suppose this is the level 2 pipe and I'm going to look from above. I can only see level 3, which is a red colored pipe, but there is actually a level 2 pipe beneath that, but you won't be able to see. Why? Because we're looking from the top view. Is it clear? So always whenever you're going to see any particular drawing of related to chill water piping in the HVAC segment, you have to understand that when you're looking for the drawing from the top, you will be looking only considering the return pipe. That means only level 3 to level 1 flow you can see. But you also have to design level 1 to level 2, that is supply. So designing is going to look like this different. This is like a section drawing that I'm drawing before you. Agar yahi same cheese if I'm going to show in the top view or the this one total top view, you cannot see the gray colored lining at all. Is it clear? So inside the drafting parameter, we have to give from level 1 to level 2 and also from level 3 to level 1. Now depending upon the levels is what is your fittings going to work. Alright, because the water that is the riser here, it is going to take a turn and it is going to be in the same level. So if the pipe is going to be in the same level, just taking a turn, I can use 90-degree elbow. If it is going above and then it has to move above, means water was flowing until like this. This was level 1. It is taking a turn above and then moving into level 2. So there is an upliftment here, right? So there is a height increased for level 2. So this particular segment here is not going to use my same 90-degree elbow. It is going to use a dropper, downward dropper. All these I'm going to show you. All right, all the fittings I'll be showing you. You're only understanding now. Then after this particular thing, what you have next is if you're returning. So when you're returning, you see it is from level 3 dropping directly to level 1. From level 3 to level 1. So there is a throw of water. So here also there will be a different fitting, same like this. And then it is coming down. It will be in the water has to again from 3 it is now flowing into level 1. So it will not be taking the 90-degree elbow. Same kind of an elbow will be applied here. And then the water will be flowing inside the chiller. Aai baat samajh mein? So if you don't understand levels, you won't understand fittings. These are only some nominal fittings that I have told you. You will be getting a T section, a dropper T section inside your plan. Okay. Now, for example, I'm going to give a small test. That is to understand if you have understood the complete setup. What I'm going to do is I have created one complete riser this way connected to the chiller. Try to consider this as 500 TR. You're going to calculate that in terms of GPM. And I'm going to connect first, second, third, fourth. 1 AHU, 2, 3, 4. This is the chiller, we already know that, and I'm not taking any supply and return. That is understood now, the connections. I'm only naming AHU1. This is AHU1 6.5 TR. Every calculation is supposed to be done. AHU2 is 7 TR. AHU3 10 TR. AHU4 8.4 TR. Now I want the GPM reading for individual, starting with the chiller. 500 TR, how much? 1200 GPM. For AHU1, 6.5 TR. 15.6 GPM. Yeah, Mr. Sriram, you can do this one. What do you say? Recheck. Yeah, let Asad do the calculation. You recheck if it is coming correct. Yes, 70 R. 16.8 GPM. Okay. 10. It will be 240. 24. Okay, 24. Last. 8.4. 20.16. Now individually tell from the table the pipe sizes for individual AHUs. That is this connection. This is I'm just shown one connection, but it is indirectly two connections. Otherwise I'll draw the two connections for you. Supply and return both. Yes. For 15.6 GPM size. 32 mm. Okay, next 16.8. 32 mm. Next 24. 40 mm. 20.16, 40 mm. Shriram, it is rechecked properly, all correct. And for this one, 1200 GPM for the chiller riser pipe size, that is going to be 200 mm. Right. Now you see, I'm going to minus each and everything from 12,000 GPM. Keep your calculators ready. Minus 15.6 GPM first. Then you have 16.8 to minus 24 minus 20.1. Tell me the last remaining amount inside the chiller. How much gallons is present? Mr. Sriram, please check. 1100. तो अच्छा वैसा है. Please do the calculations once again. Reconfirm. Correct? 1123.44. Now check for 1123.44 what is the pipe size? Same 200 mm? Right. So what you actually now have to do is, I'll just increase this in size to delete very quickly. So that was 1123.4 and 1200 GPM. Size for both is coming 200 mm. Right? So now with 4 different connections inside the AHU, the main riser size is going to remain the same, 200 mm, because water is reducing inside the content of the chiller, but the size will depend if the JPM is totally going to be down. So now the question rises, if it is going to happen like this, what size should we actually keep for the riser? The one that is after supplying to different AHUs or from the starting? What would you do? We will consider the pipe size depending upon the capacity of the chiller first. Later on, depending upon the segment where the chillers are only, where the AHUs are only available, if you have the capacity to reduce the pipe size to depended upon the 4 calculated AHUs. Now after doing the subtraction, next task is to add all the 4 AHUs and tell me the final GPM. I'm going to write here the sublimation of that one. 15.6 plus 16.8 plus 24 plus 20.14. Very, very quick. $75.54. Confirmed? That is the total GPM. 75.54. Chalo, 5654, same. Now check the pipe size for this one. 75.54 or 56. It comes to 65 mm. Now the same situation what you have to consider is, because suppose this is going to be the last portion where the chiller is supplying to the 4 AHUs. Uske baad there are no AHUs, there is no supply, there is no return. That is the last segment. So in that situation, what you should do is you should not keep your riser dependent on 200 mm of pipe size of the chiller. Okay. You can make that as a riser from here to here. That is for showing that the water is entering. But the other header, what it is getting connected to the chiller AHUs individually, that can be confirmed depending upon the last capacity or maximum capacity of GPM flowing inside individual AHUs. Now for 75.54 GPM, capacity of the pipe should be 65 mm. So if I'm going to keep the header 65 mm, it is better, or if I'm going to keep the header also 200 mm, that is better. 65 mm is better. Why? Because we are saving the cost on the material of the pipe. Is it clear? We have to check the initial as well as the running cost. And in chiller, we know that the machine is having the least or most less maintenance cost. Why? Because initially everything is going to be set up in the design. It is not like the DX system or the other central AC ductable package systems. Fine. So that way you have to keep and remember so many calculations. Now see, chill water piping is having more things to remember rather than the ducting and the SLD and DLD of the ducting. Is it clear? Now when you know about all these things, any confusion in this one? Is it totally clear how to make the calculations? Each and every calculation you will be coming at individual timing. Okay, how to do that one. Now the next thing that you have to understand from the notes, page number is 26. Open page number 26, chill water pipe drafting. In that one, you have to highlight and understand that the chill water pipe drafting is going to be totally similar for air-cooled chiller and water-cooled chiller. Now, before we proceed with the actual single line diagram inside the connections, what I'm going to understand or make you feel is the precautions that you have to do while doing the SLD drawing. That is, you cannot run the pipes anywhere as you like. There are some precautionary measurements. First point is the chill water pipe should not run or go through the structural parts like beams and columns, etc. You cannot disturb the structural conductivity of the building for running your pipes. Fine. So they cannot run like from beams and columns, etc. But they can go through walls, but not in a continuous manner. How is that? The chill water pipe should not go through the wall continuously. You can just break the wall, make a hole, and then you can proceed. But breaking the wall that way and then totally coming, dragging the complete, disturbing the complete elementary situation or the elementary function of the wall is not purpose. All right, because you're totally breaking the bricks. How are you going to actually understand where the pipe has to end? The wall will become very weak. Clear? So you have the diagram here. You can see you can create a hole and continue, but not disturb the construction. See, this way you have taken the pipe. In the first diagram, you have taken the pipe and you are moving totally laterally in the direction breaking the bricks, which is incorrect. But the correct procedure is you can make your pipe flow through one end from the other end. Making it left and right connection is not possible. Okay, you have to keep these things in mind. Last point, the distance between CHWS and CHWR, that is chill water supply, chill water return, after installation should not be less than 50 mm. The total distance between the pipe after installation should be not less than 50 mm. Matlab minimum should be 50. You can keep above that. Though I'm going to consider 1 feet, 300 mm. I can use that, but I cannot make it 25 mm. Both the pipes will be stuck together. There will be no place for thermal efficiency to lead. There will be no place for your energies to confront. There will be no space for changing the material of the insulation at the time of maintenance. Correct? So should not be less than 50. It can be more than 50 after insulation. Please highlight, very important point. Lastly, we can get the riser stack from the civil duct after the opening of the building. You'll have to contact your civil contractor for letting you know where is the opening of the building so that you can place the chiller, and then from there you can take the pipe through the OTS. All right. So these were all the important points that you have to remember. Now we are going to actually do the piping inside the plan. So for that, what we are going to do is we are considering the drawing, and you can see there are some cars available. There is a symmetricity of the drawing. The right hand side portion looks similar to the left hand side, right hand side, both look similar. This looks the entrance, this having the stairs and etc. And we are considering this is going to be the civil shaft. So we have placed our chiller there, and inside the chiller from the top you can see where the connection, supply and return is available. Correct? So the green color thing is the supply, red color thing is my return. You see the return is outside, supply is inside. That means if you're going to look from the outside region, if I'm standing at this position of my chiller in this location and trying to look at the project, which is the first pipe I'll try to see? Red color one, right? Because I'm standing at this particular location. Suppose I'm going to draw a line. I'm standing here. And if I'm going to stand and look at the pipe connections, the first thing is the red pipe. Even though the green pipe is there behind, the only red pipe will be visible to my vision, right? So this is my particular chiller where it is placed. I'm going to zoom out and you can see all the blue colored things are my AHUs. They are possibly available in different locations. That is as per the design consideration that is provided to you. All right. Here what I'm going to do is try to remove these pipe connections, because we are going to do that again. That is the lastly submitted project by the last batch. These AHUs are having the content, means what capacity they are. 3.3, 5 TR, 4 TR and 3 TR. Fine. So you can see these are left empty. So this much position or this much space is for assignment. You give your own quantity for the AHU, decide your own pipe size and let me know how you have done the connections. Is it clear? So for that particular thing, I have left these 4 AHUs in 4 different places unentered. Next, what we are going to understand is we have a catalog table here which is going to give us all the fitting details. And the drop down elbow that I was telling you is this particular thing. It is going to connect with the pipe from this end. It is going to move above and then flow down. If I'm going to tilt this and put the other way, it will take from above, pull it down. If it is in this position, it will take from below, put it in the side. That's why 90° downward. The other one is 45° downward. It's dependent upon the angle. After that one, what you have is 45° normal elbow and 90° normal elbow. The one that takes a turn for equal levels and similar levels. This is your riser stack or the opening of the pipe, how it is going to look like. Fine, from the interior. After the hatching, it looks like this. You have different amount of reducers. You can see each and everything is mentioned with a size. Now for the diffusers, this is 80 by 64, so 65. So which is 80, which is 65? The other end, that is the mouth, is 80 and the other end is 65. That looks smaller. This is 100 by 65, 100 here, 65 here. Similarly, that way we have something for a T-joint. So the T's are going to be connected in those positions where all the 3 pipes are running in the same level. Suppose my main level 1 pipe is running from this side and also the water has to move the other side, and in between, in 3 different directions, water is running in the same level. Remember when I say about levels, if it is level 1, you can apply that. Level 2 alone, you can apply that. If level 1 and level 2 are in connection, you cannot apply this. Lastly, you have the dropper T that we are going to use, which is going to give you not in the equal levels, but in different levels. You can see something is lifted up here. So a pipe of level 3 will come, drop into this, and it can supply in the below level. That can be supplied, that can be returned, depending upon the situation. All right. So this is all about different categories of the catalog pieces that you have, and this will be generated and created only and only on scale of 100. It will be provided to you by the manufacturer whose manufacturing fittings you are going to use. You should never try to move any of these catalog pieces. You cannot use the M enter command and move them for using inside your drawing. You should only copy them, because you will have to totally change the scaling depending upon your design and your pipe size. Now I'm telling you that it is totally made on 100 mm. My pipe size is only as per 12 GPM only 32 mm. How can I make a fitting of 100 mm on 32 mm? Possible? It is not possible. So you'll have to scale that particular thing to make it to 2 mm and then connect inside your pipe. Fine. So there is a lot of work that you have to actually do. Inside this particular fitting here, what we are going to do, if you're going to zoom in at the chiller and start to do the chill water supply and return, before that, once you start the project, try to click on the layers and check how many different layers are applicable inside your drawing. You can see there are so many different layers available to you, and because of that is what the drawing looks this way. Now you cannot actually ask a question that said, how did you draw the car? We are not having to do anything with the car. That's in the parking area or in the placement. All right. So what we are actually having to do is only with the chillers, the chill supply. So we are considering inside this complete project to do the chill water piping in the left hand side of the building, which is a waiting launch area of Terminal 1. This whole thing is Terminal 1. Present day situation in Dubai Airport, it is exactly the same way. And this is a still empty file. I will be showing you the completed HVAC drafting file of this project. And you can see how beautifully the ducts are connected, exhaust ducts are given the connection, everything. It is very good experience for you to sit and study that plan only. Minimum 2 hours you will require to understand the complete plan. Minimum 2 hours. 2 hours it will take for you to totally zoom and read how, from where the water is coming, where the air is supplied, to which zone, how much of CFM is going. Minimum 2 hours. It is only then that we can say that you are professionally, technically sound in the HVAC designing process. ठीक है, so you have to take a little bit of initiation and interest, otherwise नहीं होगा. Fine. So from here what I'm going to do is we are now letting us understand how to do the SLD creation. So for that, if I'm going to zoom in and click on my this connection, you see it says the layer created is CHWS, chill water supply, and this one is CH, not connected there, but you will be having a layer for that. Sometimes layers don't really work correctly. There is WCHR, that one. So this is my WCHR. This is WCHS. Yeah. So this is different and this is different totally. All right. And currently we are in using legend as the current layer. So I'm not going to use that one. I'll try to use my layer as a current layer. Before you start doing the chill water pipe, you need to select it and delete. Otherwise also it will be deleted. You don't really need to do that. I can delete this one also. I only need the segments. It is not necessary that the return connection be below or the supply connection be above. They can be in the same level as well. Like this. Is it fine? Now if I'm going to check what is the distance between the center point to center point, you can see how much is the distance between them in x-axis. 300, nearly 300 mm of distance between the two pipes, between the two risers. That is how much feet? 1 feet. I'm keeping that for proper understanding so that you can actually understand how it is going to be. All right. So now what I'm going to do is I'm going to keep my ortho turned on, keep my layer active. Here the layers are going to be very, very important. And you see inside the complete plan, these kind of symbols are your structural elements. This is going to be the column. This is going to be the column. This is going to be the beam. I cannot actually move the pipe from these ends. I can try to drag that between the walls. Now what I want to do is I'll start the pipe from here and until I reach the last AHU. Till here I want to make the piping very, very proper, very, very simple, very, very crisp. So what we're going to do is we can come out with different methods of giving the piping, same like how we have done the low terminal design ducting. The best possible is to keep it the most simplest. Let me use PL enter, Polyline, start from this end, and I'm going to drag it a little bit until this position here so that I can break through the walls in the side. I'm going to click there and you can see this is the first wall that I'm breaking. Okay, I'm not moving continuous on the other end or this end. I'm just making a hole and moving forward. Now I can have multiple walls ahead and I can keep going through that this way. I cannot stop here and try to take on the straight line. Why? Because what I have there? The door. See the structural element. If I'm going to suppose click until this position and can I move till here? I have a column there. So what I need to do, I need to drag the line more further, right? So what I'm going to do is I'll click this up, extend this until this segment because I need to get into the wall because I have to take a space from the wall, right? So from there, use Polyline again. And then you can do that one. You are breaking through the wall. That's possible. How many walls? 1, 2, 3, 4, 5. And from here until where do you have to stop? Can you go there and then take the turn? It's not necessary to take the pipe of so much of length because you're wasting the material. This is the HU. Just above or very, very close to the HU is what you can click once. And then you can go this way because you're going to break through the next wall. And don't really feel that you're breaking the door again. The door is only a symbol which will be closed and door is below the false ceiling. This is all that is happening above the false ceiling. All right. So the wall is going to break. This one connection will be getting to this AHU. I need to take care of this AHU also. From here is where I need to take a turn. Now if I take a turn, see below that will I be reaching the last AHU if I take a turn from here itself? The pipe will be very close to the last AHU and we cannot change the position of the AHUs. That is given by the mechanical engineer. What I can do is I cannot move this way and again I can move down. In between I'm getting a column. Not possible again. So I need to drag it outside. Click there. come here. Now this particular section of the drawing is applicable for this AHU, this pipe. I can give the connection. Now if I'm going to move little more below the pipe that I'm keeping the riser pipe, this is also AHU is covered in this one. I can give the individual connections there. And lastly, I'm having the last position and the final AHU connection. So I can drag until this position or this position to keep it for letting the water totally drop with force downwards. Or I can try to manage with the end of the AHU. I'm going to not waste the too much material. Click here, move this way, and I'm going to leave that until this position like this. So this is the complete. Now who can tell me which level pipe? 1, 2 or 3? This is total level 1 pipe. It is starting from the chiller. Not even one AHU is connected. The moment we are connecting AHUs, which level that will turn? 2. The moment I'm connecting the return, it will become level 3. All right. So from here you can see if I'm going to select this, it is a total polyline that is from there, and because we had to break that here, what I'll do is I'll try to join those. And the whole thing is selected at once so that it will become easy for me to take the offset. Why am I going to take the offset? For the return. I don't want to keep tracing the return again of the same level, and maybe I will not get exactly 300 mm. Right? If there are considerations like this coming in between, now see exactly at 300 mm, maybe this is a joint where it is going to fall. So I cannot go there, and because of that return pipe, I'll have to change my supply pipe. So I cannot do the tracing for the return. Instead, what I can do is offset for 300 mm. How did I come to know about 300 mm? Between the center points of your risers, you first have to check that before giving the offset. Otherwise, you will not know what the offset you have to take is. Is it fine? So that way you have to do the designing very, very, very keenly. Now what you can do is match this with the next layer. This way. And it will be, your return is also done. Now you have to check for the return pipe if it is breaking any of the structural element. If it is doing so, you'll have to change. See here, not breaking. Here also not breaking. It is taking exactly like the wall. Here also very clean. Here also clean, and here also done. Level 1 is completed for supply and return. Now I'm going to level 2 first rather than directly jumping to level 3. In level 2, considering this particular HU, suppose I'm going to call this as 1, 2, 3, 4. This is the last HU, number 4. 1, 2, 3, 4. I'm going to start with number 4. So it will be, I'm going backward, 4, 3, 2, 1. Fine. So here inside the HU, which is named as 3TR, look at the HU and tell me which is going to be the supply, which is going to be the return. The two connections that is given here. Observe very, very carefully, because if this stage also not able to understand the drawing of an HU, is very, very difficult for you to then move forward. I want to understand which is my supply connection, which is return connection. Left one is a supply, right one will be return. Can you please give me some explanation why and how did you understand that? This can also, for making you understand that, I'll have to actually give you the schematic diagram of the HU again. This is HU in a section view. I'll take the green color. I told the supply is below. The return is little above. As per the design set by the HU, by the manufacturer. In between you have one more thing. Which pipe is this? It's all related to pipes. There is no ducts now. This is supply. This is return. What is this in between? You have all. No? Yes, it's called the drain cock. If any excess water condensed or available at the corners or surfaces of the HU or any other component of the HU is going to fall from the drain cock. Fine. So this is going to be your drain pipe. And because this is a return, the return is always behind or the close to the filter of your HU. Why it is going to be like that? Because the return is first going to come from here, get sucked, and then it is going to be absorbed and then compressed, right? So anything that is close to the filter is going to be your return pipe connection. Now this is my filter. The closest to the filter is return, and this will be supply. All right. So always remember that way. It becomes very easy. The filter will be marked like this, which some kind of a hatching, because otherwise you won't be able to know where to apply the duct from. It can be duct will start from other side and this side. Total demonstration will go wrong. So the filter or the back portion of the HU will be given like this. Any connection that is close to the filter is going to be the return. Now if I'm going to select this and I'm going to mark that with a different color like red, I'm going to select this. I'm not changing the layer. I'm just changing the color, green. Very, very comfortable to understand. Green marks the supply, red marks the return. Now coming to this AHU, it is a little different. Tell me the return and supply. Left, left is the return, right is the supply. Understood? This here, this is return. Supply. Close to the filter is always the return. Lastly, this side. Done. Fine. So now depending upon the coloration and the indication of supply and return is where you have to join the lines. Coming back to the same polyline, from the center point, you have to go till the green pipe or the red pipe? Only till the green pipe, because till there is only the supply limited to you. It did not come straight. Ortho is turned on. PL enter. Maybe I'll try to demonstrate this with some amount of width. Level 2 pipe. I'll give 25, 25. Becomes a little thick. TR double enter. Trim this end, trim this end. Level 2 is connected to my level 1. So supply until this the riser, and here it is supplying into the HU. This becomes level 2. Now what about the red one? PL enter, keeping ortho on. From the midpoint, green pipe or red pipe? Red pipe. We do not turn the layers off. This is which level? Third level. Where is the return? From which machine the return is coming and going to where? From the AHU it is going back to the chiller. Alright, so in supply the water is falling. In return the water is moving above against gravity, and this is towards gravity. Remember that. These are the scientific terms that you need to understand. Alright, so every turning here requires the fittings, elbows and etc. Here also, here also, here also. Fine. Coming back to this position here, I have a supply and I have a return to be connected. First I'm going to connect the return. Maybe till this end. The return, so it has to go till this side. Select and match with my layer. Can I do offset of directly 300? But do we know that if this is a distance 300 or not? I need to first check that one. DI enter this end to this end. How much it is? 300 exact. So I can take an offset. Offset for 300 mm. Connected. You see it connects normally and automatically to the same generation because of leaving the gap here. Alright, so you can try to modify that if you are going to make the connection to the supply. Drag that one till this end. Match with the layer, and you can increase that in height. Until you get a straight. Also done. Here there is direct connection, so we'll take PL enter first, select the midpoint, come till here, drag it outside, that is connected, change the layer, come here, PL enter, center point, keep ortho turned on, red to red, that is done, TR double enter, trim the extra lines, and once again PL enter. We are into the red layer, so I'll first match with the red, change my layer, center point, zoom out until this end, done, TR double enter. This is trimmed, this is trimmed. So all the HUs are now connected properly with levels and everything. Here also you can see, if you are zooming out, you can see how neatly is my pipe gone and connected. Is it correct? Now what we have to do is we have to do the inside homeworks. That is nothing but for each and every AHU we have to provide how much is the GPM. Depending upon the GPM, how much will be the pipe size. Clear? So very quickly, I'm going to start that from the chiller. I'm going to consider a chiller of text 850 TR. How much is that GPM? 850 TR, 2.5 into 2.4. How much? Please tell me. 2000? 2040 GPM. That is completed. Now coming to individual AHUs here, it says this is 3 TR. How much would be the next 3 TR GPM? 7.2 GPM. And how much is that pipe size going to be? 1 minute. Okay, we'll first mark all the AHUs with the chill water pipes. I actually also need to mention the CFM. So tell me how much is the CFM for 3 TR? 1200 CFM. Confirmed? All right. Copy that. Next is 4TR. 9.6 GPM, right? 9.6. Mr. Mary, are you following? 1600 GPM. Save. Next. 5TR. 12 GPM and 2000 CFM. .3 TR. 7.9 GPM. This one. CFM. 1320. You can make the calculations for all those ones. Now coming back here, back to 3 TR, that is AHU4. 7.2 GPM. Tell me the pipe size. How much? 25 mm, right? That is 7.2. So what we are going to do is we are going to mark that, but with the diameter symbol for the two pipes. How we are going to do that means I'm going to change the layer. I can take any text layer available with me. T for text. I have text that is in green. I'll take text duct. We are going to first draw a ellipse, circling the two like a rubber band. Okay, using my LE enter, that is a leader line, indicating the marking what is the actual size. I'm going to copy the text once again, place it here. Yes, so for 7.2 GPM, that is having the diameter of 25 mm. So the diameter symbol, how you need to apply is shift plus 5 number and the alphabet C, and you will get the phi symbol. Yeah, 5C, shift plus phi, that is phi is percentage. So shift plus percentage, and no shift and C, directly C. You'll get the phi symbol. That's a shortcut. You can note it down. That is 25 mm is the pipe size. I'm going to close that. with a different coloration. I'm going to make it with magenta. Okay. Next, 40R 9.6 GPM pipe size, 32 mm. So EL enter, LE enter for the leader line, CO enter to copy the text, place it here. Yes, how much is that? 32 mm. That's the diameter symbol. Once again, EL enter, the two different levels, LE enter, copy the text, that is for 12 GPM, 32 mm, same right? This side 3.3 TR, LE enter, CO enter for copying the text. How much? This is 7.9 GPM, 32 mm, right? Okay, so we have three different or three similar pipe sizes. Only the last one is 25 mm. Clear? Now, what would be the actual size of my rise as per 2040 GPM? Find from the table. How much? 250. Pipe sizes 250 mm. Is it clear? Each and every one, each and everything. This way you have to present the SLD drawing which the engineer has to do, which you have to do. It is your responsibility. How to update that with the fittings, with the annotations, with the next connections is totally going to come inside your double line drawing. And this is all about doing the single line drawing. All right. So is it clear? So this way I'm going to now save this particular file with the on desktop. This is chill water piping HDE 92 SLD. That is saved totally. The concept is clear to everyone. The level understanding is clear. The calculation is, so you have to keep keen interest and you have to do that very well. I'll be sending you this file. What you need to do is first turn all the layers off where you have done the chill water piping. The green, the blue, the red, the pink and everything. Keep selecting, just turn off them. You know how to off the layers, I believe, layer on and off. Make a copy of this only as XREF so that you can use multiple times for practice. All right. Turn off all the layers, save that with a different name in a new drawing. export that as XREF and then do your drawing. Is it clear? That is the purpose of not giving you the XREF, for you to understand how to create XREF. All right, because everything, if I'm going to give ready-made, it will become a habit for you. I want you to keep working out for it. You should generate the ideas. Fine. So now this